Good morning and welcome to our science lesson. Now, in our previous lessons, a couple of lessons that we covered, we looked at waves and the properties that are exhibited by waves and how we can be able to apply them in our daily lives. Now, today, we want to single out light and discuss all the properties that we looked at in relation to light as a wave. Probably, before we move on, it is good to point out that light is actually an example of transverse wave. And being transverse, it is also good to note that it does not require a material medium. It does not require a material medium of transmission. Now, a transverse wave, we said, is one that is characterized by a series of crests and troughs. And we did plot time against displacement. Where we were able to point out that a particle in the path of movement of a transverse wave is actually displaced in a direction which is perpendicular to the direction of motion of the wave. That is to mean, if this one was the direction, if this one was to be the direction of the wave, if that was to be the direction of the wave, then we expect that our direction of motion of particles along this wave train will be perpendicular to that of motion. So that if a particle was here, we expect it to oscillate in such a way that its displacement is always perpendicular to that of direction of motion of the wave. Note that this wave is actually progressing from the source to a place far away, or to a point far away. That way, we are sure that energy that was transmitted as a disturbance is actually flowing to another point away from the source. Recall that in general, a wave is actually transfer of energy in form of disturbance. Take an example. When you throw a stone into the water surface, you will expect that there will be some circular waves that will be generated from where you throw the stone, and they progress away from the source, so that now you have a wave train that is moving in that direction. That one in itself is an example of a transverse wave. Now, light in itself has many uses in our daily lives, but for our definition, we will define it as a form of energy. A form of energy that makes visual perception possible. You imagine of a situation where you would be requested to observe something where you have not been provided with light. That one is completely impossible, because for you to be able to observe something, this form of energy that we are talking about should come from a source, travel to your eye in form of a disturbance, because in itself is a wave, and when it gets to your eye will actually act as a fixed reflector. That way, it's going to be reflected, and when it is reflected by your eye, it superimposes itself on the first wave. What results is actually a stationary wave, which is a straight line. That way, you will not observe the object you are trying to observe in form of crests and trough. Rather, this stationary wave, which in itself is actually a straight line, will actually help you to observe what you are after. Now, light is also important. It's also important in the process of photosynthesis. In the process of photosynthesis, you find out that plants will actually make use of light in order for them to manufacture their own food. Now, let us think about sources of light. And here we are going to classify them into two. Now, depending on whether or not a source produces its own light. We are on sources of light, and we are saying, depending on whether or not a source produces its own light, we can have the following sources. Number one, or the classes are as follows. We have the luminous. We have the luminous sources of light, and these ones actually produce their own light. We have luminous sources as one of the classifications that we have, and a luminous source is one that produces its own light. I will give examples. You could talk of the sun. You could talk of stars, glowing worms, electric bulbs. You can have television screens. Probably we can add a burning candle. All these are sources that are able to produce their own light, and that is why we call them luminous sources of light. We could also have another class of sources of light, which we will call non-luminous. And these ones do not produce light of their own. And these are actually the materials that we say produce or are observed when light from a source bounces off from their surface. So therefore, for them to be observed, you expect that light is going to go through reflection, because you will observe it when light from a source falls on it, bounces to your eye, and that way you can actually observe them. I'll give examples, and examples are wood. You will see a piece of wood when light from a source is reflected. You can talk about a blackboard. Probably you can talk about your shoe. You can talk about a suitcase and anything else that you know which does not actually produce light. Now, let us look at beams and rays of light. What is the difference between a beam of light, a ray of light? Because these are two terms that people tend to use interchangeably, although they actually have different meanings. Probably we can start by defining a ray, and this one is a path along which light energy travels. It's that path along which a light energy is going to travel. You could also define it as a path of motion of a light wave train. It could also be that path of motion of light wave train. Now, by the light wave train, we are not interested in the way we are going to have our particles displaced. Rather, we know that being a transverse wave, we expect it to have a series of crests and troughs, although the path of motion is actually from right to left. That way, the path, this is the path that we are interested in. In which direction is our light as a wave progressing to? That one is what we call a ray of light. Other characteristics are going to be exhibited, and they will help us to discuss other properties of light as a wave. But if we want to narrow down to a ray of light, then the direction to consider is the direction of motion of the wave itself. Now, we could also define a beam, but before then, it's good to mention that a ray is represented using an arrow whose head points to the direction of the wave. This is what we mean, that we draw an arrow and the head points to the direction of motion of the wave train. Now, in itself, it's a path of motion of the light as a wave, but should have a head which should inform us on the direction that our wave has taken. The direction that our wave has taken. Remember that a wave is actually a vector. A wave is actually a vector. This one is to mean that magnitude of or the size of this arrow should actually tell us something about the intensity of the light, whereas the arrow gives us a sense of direction. That for you to be in a position to describe this wave fully, you ought to give us some information about the direction, which is going to be suggested by the arrowhead, and then you will have the magnitude, which should inform us about the intensity. How strong is our light? How strong is this light of ours? Okay, let us define a beam of light, and this one is actually a stream of light considered to be a bundle of light rays. That when you have many rays going towards or pointing towards the same direction, then they cease to be rays. Now we give them the term beam. of light, and they should have the same direction, and probably because they are from the same source, the intensity should also be the same. Now we can have some types of beams of light. Number one, we can talk about a convergent is one where rays from a distant source collect at a point. That a convergent beam is where rays of light, remember that we said that when we talk about a beam, we consider several rays of light. In fact, we call a beam a collection or a bundle of rays of light. Therefore, if some rays from a distant source seem to collect at a point, then we talk about it as being a convergent beam. That they seem to collect at a point is an example of convergent beam. Rays are coming from a distant source and collecting at a point. Note that their direction and magnitude should be the same, which means that because they come from a monochromatic source of light, now they have the same intensity. They have the same intensity. That is why we claim that the magnitude is the same. How about the direction? The direction will also be very important because our beam is actually a vector quantity, and therefore for us to claim that the rays are actually equal, they will have to possess the same direction. We could talk about another, which we call divergent, a divergent beam. What kind of a beam is that? And here is where rays from a point source spread out as they move away from the source. That we have a point source of light. It produces rays of the same intensity, but as they advance away from the source, they start spreading out. So you will expect to have something like this, that you have a common source, but as you advance, your rays are actually spreading out. Now, note that the sense of direction here is also very important, because suppose you were to reverse the direction of the arrowheads, now what you would have drawn would actually be a convergent beam. Therefore, the key word here is that your rays are actually spreading out as you advance from the source. Lastly, we have what we call a parallel beam. A parallel beam, and here rays from a source move away in such a manner that they are perfectly parallel. That the rays of light are actually perfectly parallel to each other as they move away from the source, something like that. So that now you have a bundle of rays of light. And note that these rays are going to have the same direction, the same magnitude, because they come from the same source. Therefore, as you draw, be careful about the sizes of your path of light. Now, depending on how materials receive light, some will let light pass through them, some will actually reflect light, some you will have light pass through them, but you might not see through them. We have the following types of materials. We could talk about types of materials, and this one is dependent on whether or not they actually allow light to pass through them, and if they do, can you see through them? Now we have opaque. We have what we call opaque objects or materials. They do not allow light through them at all. But no light, absolutely no light is going to pass through them. For examples, you can talk about yourself. The human body will not allow light through them. You can talk about a stone. You could talk about bricks. You can talk about wood. And the list is endless. You can think about several that cannot allow light to pass through them. There are actually very many. Think about others and add onto the list. That's opaque object. Number 2, we have what we call translucent materials. And these ones, they will actually allow light through them, but you can't see through them. That they allow, but we cannot see through them. They allow light to pass through them, but you cannot see. For example, if you have a greased paper, okay, you could talk about other pens that you use in toilets and bathrooms. Pens. By the way, these ones are not too many. You can also talk about a frosted glass. Frosted glass. These are just a few examples of translucent materials. And when we talk about a translucent material, we have agreed that it is one that will allow light to pass through it, although you can't actually see through it. And lastly, you can talk about the last category of materials. And we call them transparent. Transparent materials. Transparent materials will actually allow light to pass, and we can see through them. We can actually see through a transparent material. For example, you can talk about ordinary pens, and you can talk about car windscreens. These ones are examples of transparent materials, and you can also think about others. You can think about others and add onto the list. Now, having said that, I want us to advance now and discuss the properties of light as a wave. Now, one thing you are going to appreciate about light is that we have observed, even from the path of light, that actually light travels in a straight line. Light travels in a straight line, and that is why we represent the path as a straight line with an arrowhead to show us the direction of motion of the wave train. Now, we start by discussing a property that we call linear propagation of light. And this one is the simplest property and refers to the fact, that light travels in a straight line. Just the mere fact that light travels in a straight line is what we call rectilinear propagation of light. Now, If that be the case, then what happens? Because we have looked at different types of materials, and we have appreciated that there are some materials that will allow light through them. You could see through them, some you can't see through them, and others will actually not allow light at all to pass through them. Therefore, if light from a source comes across something that cannot allow it to pass through, what will happen? Now, when light comes across an opaque, when light strikes an opaque object, what happens is that a shadow is formed. A shadow of that particular body or material is going to be formed behind it. That is to mean that light in one way or the other has not passed through it. Now, therefore, a shadow is actually a phenomenon that has been used to explain the fact that light travels in a straight line, and that when it is obscured, or when the path of light is obscured by placing an obstacle in form of an opaque object on its path, that is when a shadow is going to be formed. Therefore, we can discuss in relation to this, we can discuss shadows briefly. We can discuss shadows as a result of obstruction of the path of light. That a shadow can simply be defined as that obstruction, the result of obstruction of a path of light, and that one can only be caused by an opaque object. Remember, we have said that the other types of materials can actually allow light through them. Some you see through them, some you can't see through them. Now, depending on what light comes across, that is when we can discuss shadows. Now, there are some factors that affect the type of shadow formed. There are some factors that will actually affect the type of shadow formed, and they are about 3. Number 1 is the size of the opaque object. Remember here, we are actually narrowing down to opaque objects only, which is to mean that when light comes across a transparent or translucent material, we do not expect a shadow to be formed. Number 2 is the size of the source of light. size of the source of light. And lastly, we have distance of the object from the light source. Distance of the object from the source of light. Those are basically the three that will inform the type of shadow formed. Now, we will appreciate that probably we have a point source. A point source concentrates the rays of light, and therefore, if you come across an obstacle, all the light is going to be obscured. All the light is going to be obscured, and therefore, you do not expect spillovers to pass through or to pass over the obstacle and light up the shadow that will form behind your object. That way, you are assured of a totally dark, uniform shadow. That if you have a source of light, it's going to be concentrated over a very small area, and therefore, all of it is going to be obscured, and that one means that our shadow is going to be uniformly dark. Okay, sometimes you could have a bigger source and it spreads out the light. Probably your obstacle is quite small compared to the area or spread of the light. That one means that behind your object, you are going to form a shadow which is having a very dark center, and is going to be surrounded by a ring. Is going to be surrounded by a ring so that the center is completely dark and the ring around it is a bit lighter. And that one brings us to the types. This is a ring of brighter shadow. Can draw that one better. That you are going to have a very dark center surrounded by a ring of lighter shadow. Or remember that a shadow resembles the shape of the obstacle, and therefore you will have a smaller shape of the obstacle at the center, which will be totally dark, and there will be something brighter around it. And that brings us to the types. Types of shadows. And we have one, what we call the Umbra. And this one is a uniformly dark. It's a uniformly dark shadow. Formed when all light from a source is obscured. It's actually a totally uniform dark shadow. Let us add total uniformly dark shadow, and it will be formed when all light is obscured. We have looked at a point source coming across an obstacle. So let us have this source of light spread out, and on its path, when we have an obstacle capable of obscuring everything, this one is an obstacle, then you will have something that resembles your obstacle, which is now the shadow behind it. Again, this shadow is going to be totally dark, and it's going to resemble the shape of your obstacle. So this one is a total or totally dark shadow, or what we call the Umbra. This one is your obstacle, and this one is your source of light. Source of light. Now, still on types of shadows, we can have number 2, what we call the Penumbra. And the Penumbra is a totally dark shadow surrounded by a ring of a lighter shadow formed. This one is formed when some light spills over the obstacle. That sometimes the size of the obstacle might not be too large, and therefore you expect that some rays of light are going to spill over from the the obstacle, and that way you will have a totally dark center, and this one is going to be surrounded by a ring if it comes from a source of light. Then you have some light spill over. Let's say your obstacle is that size. You expect that over and under the obstacle, you are having some light that is spilling. And therefore, when you have this dark part, there will be a ring around it, and that ring will be lighted up by the spillover light. And that way, you form an umbra surrounded by this ring, which we are going to call the penumbra, and this one is your obstacle. This is your obstacle, and then we are going to have the spillover light, and then this one is the light source. Now, depending on the type of a source of light that you have, you could have a point source, you could have an extended source. Now, that informs the kind of beam that you form. The source of light informs the kind of beam that you form. Depending on the type or the distance also of the source of light from the obstacle, you could also have different shadows being formed. For example, you could have a very distant object being lighted up by a beam of light from a distant source. Now, you expect, depending on whether it's a point source or an extended source, it's going to inform the kind of beam that is going to result from it, and the type of beam now in return is now going to determine the type of shadow formed. For example, if you have a very distant source, producing convergent beam. Convergent. If you have a very distant source producing a convergent beam, let us change our diagram to that, so that now you have rays of light coming together. Now, all of them are going to be obscured, and therefore, whatever you are going to form will be an umbra, because all of it is going to be obscured. So behind here, you form a very dark shadow. A very dark shadow. Now, suppose you have the same source, but now your obstacle is a bit close, so that you have your obstacle at a point like that, for example. And then you have convergent beam. You expect that there could be some spillovers. If that be your obstacle, there is going to be some spillover light, and therefore what you form will be a dark center surrounded by a ring, which we called a penumbra, which is going to be informed by the which is going to be lighted up by the spillover light. So that now you have umbra, you have penumbra, and then this one be will be your obstacle. That will be your obstacle. Therefore, what we mean is that the distance informs the behavior of light, and we say that the greater the distance, the smaller the shadow formed, and a great distance will also mean uniformity of the shadow, because all light is obscured. All light is actually obscured. And the reverse is true. Now, the most common shadow that is formed is what we call the eclipse. The most common and the most natural form of shadow that we can afford to discuss is actually the eclipse, which we will define as the total or partial disappearance of moon or the sun as observed from the earth. That this one is a form of shadow, which is a phenomenon that happens in the solar system, but we can only observe from the earth, and therefore when we observe from the earth, we shall have the sun or the moon obscured. Now, depending on what passes between any other two members of the solar system, that one will comprise of what we will discuss in our next lesson, and we will be able to appreciate how these shadows can be formed when we obscure light from the sun. Thank you.